Welcome back. Today we'll be talking about correlation and regression, a pair of topics about paired data. This is quite interesting and intricate stuff, and while I wish we had the time to really dig into the mathematical details, the truth is that we don't. As a result, this lecture will just provide you with a conceptual overview of correlation and regression in their most basic case. If you take subsequent courses in statistics, as I hope you will, you'll learn more about the mathematics that underlies these topics, and you'll learn about ways in which they can be extended to other settings. Historically, these topics developed from the work of Francis Galton, beginning in the late 1860s. Galton hailed from a deeply impressive extended family. Among his notable relatives, the most impressive, by far, was Galton's cousin, Charles Darwin. Captivated by Darwin's pioneering work in evolution, Galton became particularly fascinated by the heritability of physical and mental characteristics. How is it that family traits are passed down and slowly altered through the generations? Trying to get to the bottom of such questions led Galton to gather enormous amounts of raw data that he then needed to organize, which in turn led him to develop many statistical techniques. Galton's ideas were then refined and extended by his more mathematically minded disciple, Karl Pearson. Galton popularized scatterplots for presenting paired data. This scatterplot, for example, was formed from real data that Pearson collected on the heights of fathers and sons. Each dot in the scatterplot corresponds to a particular father-son pair. For example, the dot I've just highlighted in red corresponds to a pair in which the father is just under 70 inches tall. His son, on the other hand, is a bit over 70 inches and is thus about an inch taller than his father. There are 1,078 dots in this particular scatterplot, each representing a different father-son pair. These dots form a kind of cloud of points. There's obviously a lot of variation within that cloud, but we can also discern a general trend in the cloud. Namely, points further to the right tend to be higher up as well. This is no surprise, of course, it's just reflecting the fact that tall men tend to have tall sons and short men tend to have short sons. Scatterplots often have a line drawn through them. This line is called a regression line, or sometimes, more casually, a best fit line. The idea being that of all the lines we could draw through the cloud of points, this is the one that somehow fits the data as best as possible in a precise mathematical sense that I'm going to gloss over in this introductory video. In practice, we use a computer program to actually find the regression line. Our concern, however, isn't with finding the line, but rather with interpreting it. We can think of the regression line as giving us a way to make rough predictions. Here, for example, it gives us a way to predict sons' heights from their fathers' heights. For example, if we consider a father who is 68 inches tall, we might guess his son's height as follows. Starting at 68 inches on the horizontal axis, we go straight up to the regression line, and then, once we've hit it, we go left until we've hit the vertical axis. We've hit the vertical axis just below 69, so we'll predict that on average, a 68-inch man will have a son who is just under 69 inches. Now, of course, this prediction could be way off for any particular 68-inch father. After all, if we look at all the dots in which the father's height is about 68 inches, we see a wide range of heights in the sons of these fathers, everything from 60 inches up to about 77 inches. But the idea is that if all these sons' heights were averaged out, then the average son of a 68-inch father is a bit under 69 inches tall. So on average, sons of 68-inch men tend to be a bit taller than their fathers, though of course this is just a tendency. As you can see, there are still many 68-inch men whose sons are shorter than they are. Similarly, if we consider a 72-inch father, we might guess his son's height will be a bit under 71 inches. Again, this obviously doesn't mean that all 72-inch men have 71-inch sons. There are many factors that affect a man's height. The height of his father is just one of them. After all, if we look at all the fathers in Pearson's data who are around 72 inches, we see a wide range of sons' heights. But these average out, more or less, to about 71 inches. So on average, sons of 72-inch men tend to be a bit shorter than their fathers, at least in the population from which Pearson drew his sample, which was England around 1900. Okay, let's look at some context-free scatterplots. Never mind what specific sorts of paired data these scatterplots might represent. Just pay attention to the obvious difference between them. The one in the top left looks totally random, like a shotgun blast. Its points don't seem to follow a line at all, so it's not clear what the regression line would even look like in that case. In fact, it would just be a boring horizontal line. In contrast, the other scatterplot is perfectly ordered. All the points lie on a line, so it's obvious what the regression line looks like. It's the line on which all the points lie. Next, let's look at some intermediate possibilities, like this picture in the top right. While there's still a lot of variation, we can discern a general upwards trend. Points further to the right tend to be higher up, so you should be able to imagine some sort of upward sloping regression line running through that loose cloud of points. And here it is. This is even clearer in this picture in the bottom left, where the points are much more obviously clustered around some invisible regression line, which I'll now make visible. Again, I want to emphasize that we're going for a conceptual overview here, so I'm not going to discuss how the regression line is actually determined from all the points on the scatterplot. Just be assured that this is accomplished through a somewhat complicated calculation, which in practice is always carried out by a computer program. When we feed a computer some paired data, such as a bunch of father's heights paired with their son's heights, the computer can produce the scatterplot, figure out where the regression line lies, and produce one more very important number called the Pearson correlation coefficient for the paired data. The name Pearson is both to honor Karl Pearson, whom I've already mentioned, and to distinguish this correlation coefficient from other types of correlation coefficients that you might meet if you go on to take a more advanced statistics class. But for our purposes, the Pearson correlation coefficient is the only one we'll need, so I will just call it the correlation coefficient for short. But before we can discuss the correlation coefficient, we need to take a minute to discuss the general idea of correlation. We'll refine our understanding as we proceed, but let's begin with the rough conceptual meaning. Paired variables are said to be correlated if they tend to rise or fall together in a predictable manner. Let's look at some examples. First, human heights and weights are correlated. They do tend to rise or fall together. The general tendency is that taller people tend to weigh more, while shorter people tend to weigh less. Obviously, there are plenty of exceptions to this rule, but that is, of course, the general tendency. Next, fathers' heights and sons' heights are correlated. Taller fathers tend to have tall sons, and shorter fathers tend to have short sons. This is why you'd be surprised if a 5'5" man tells you that his son is 6'3", but why you wouldn't be at all surprised if a 6'5" man told you the same thing. Now let's consider another example. Among children, shoe size and reading skills are correlated. What? Does that mean that making children wear oversized shoes will help them read? Or might it mean that reading causes kids' feet to grow? Obviously not. These two variables are correlated because of a lurking third variable, age. As kids get older, they and their feet grow, and their reading skills steadily improve. The moral of the story here is that correlation is not causation. Two variables can rise or fall together for all sorts of reasons. Variables can even be correlated for no reason whatsoever. For example, it turns out that between 1999 and 2010, Howard County, Missouri's average daily precipitation was strongly correlated with the number of pedestrians killed by trains in the USA. Seriously, here's a scatterplot showing the data. Each point represents a specific year from 99 to 2010, and as you can see, the general tendency is that years in which Howard County had more precipitation were years in which more pedestrians were killed by trains. There's no reason why these variables should be correlated, and yet they are by sheer coincidence. I'll repeat the slogan a second time. Correlation is not causation. Okay, now that you have a rough sense of what correlation is and what it is not, we can begin to discuss the correlation coefficient. Here too, we'll start with a rough understanding that we will refine as we proceed. So to begin, we'll just say that the correlation coefficient measures the extent to which paired variables vary together. It measures how correlated the paired variables are. Or geometrically, we could think of it as a measure of how tightly the points in the paired data's scatterplot cleave to its regression line. A few examples will give you the general idea. The first thing to know is that the correlation coefficient is a number whose absolute value lies between 0 and 1. My concern here is that you understand how to interpret this number, not that you know how to actually compute it. In practice, we feed our paired data to a computer, and it computes the correlation coefficient for us. Let's begin by considering the extreme cases. In the top left scatter plot, in which we appear to have a random shotgun blast of points, the correlation coefficient is 0. The usual symbol for correlation coefficient is R, so I will write R equals 0 in the corner of the scatter plot. At the other extreme, we have the bottom right scatter plot, in which all the points lie on a line with positive slope. If that happens, then R, the correlation coefficient, is equal to 1. We would call this a perfect correlation, and in practice, it never happens. As you'd expect, what we actually see are intermediate cases, which will have correlation coefficients somewhere between 0 and 1. In the top right scatter plot, the correlation coefficient turns out to be 0.5. The scatter plot in the bottom left cleaves more tightly to its regression line, so you'd guess that its correlation coefficient will be higher than that. And you'd be right. It turns out to be 0.9. There's one last thing I need to mention. Our three examples of non-zero correlation have a common feature. In all three cases, the regression line is going up as we go from left to right. When this happens, we say that we have a positive correlation, which is why the correlation coefficient is itself a positive number in all three cases. But of course, the regression line need not go up. It could be horizontal, in which case r equals 0, but it could also go down. In these four scatter plots, I haven't drawn in the regression lines, but we don't need to. You should be able to see from the scatter plots alone that the general trend in each case is downwards. The tendency of the points to cluster around an invisible line is fairly weak in the top left, stronger in the top right, stronger still in the bottom left, and perfect in the bottom right. So you might guess that the correlation coefficient ranges from something close to 0 up to 1, and you'd be right, except that they all have a negative sign attached to indicate that they are negative correlations where the general trend is downwards. Thus, the correlation coefficient in the top left case turns out to be negative 0.2. In the top right, we have r is negative 0.5. In the bottom left, it's negative 0.8. And in the bottom right, it is negative 1. With all this in mind, let's go back to Pearson's data on the heights of fathers and sons. What might we say so far about the value of r here? Will it be positive, negative, or 0? Clearly, it will be positive since the general trend is upwards. It's much harder to guess the actual value of r from a picture. Even statisticians have a hard time doing that, but you probably won't be too surprised when I reveal its value, which is about 0.5. Again, this numerical value is calculated by a computer, and for now, you need not worry about how it does the calculation. We'll soon deepen our intuition about what r is telling us, but first I'll make a few general observations. The closer r is to 0, on either side, positive or negative, the weaker we say the correlation is. The closer it is to 1, again on either side, positive or negative, the stronger the correlation is. And the stronger the correlation is between the two variables in our paired data, the better able we are to predict the value of one variable from the other variable by using the regression line. This makes sense. When the correlation is strong, the paired data clusters closely to the line, so using the line to make predictions usually keeps us pretty close to the actual values. On the other hand, if the correlation is weak, then the data is often far from the line, so using the line to make predictions is less helpful. Okay, now that we've had our first pass at the meaning of the correlation coefficient, let's go over it again, adding some more mathematical detail this time. Let's return to Pearson's data on fathers and sons yet again. The correlation coefficient here is 0.5, but what does that mean? Well, it's telling us something about the two variables being related here, father's heights and son's heights. It's telling us that for each standard deviation by which one variable exceeds its mean, the other variable will, on average, exceed its mean by only 0.5 standard deviations. To make this idea more concrete, we'll first need to know the means and standard deviations of the fathers and sons in Pearson's sample, which I'll record in this table. After a lot of arithmetic, Pearson found that the mean height of the 1,078 fathers in his sample was 67.7 inches, with a standard deviation of 2.7 inches. The mean height of the 1,078 sons was 68.7 inches, with a standard deviation of 2.8 inches. Now let's consider an example. Suppose that a father, taken at random from the population from which Pearson gathered his data, is 72 inches tall. We want to use the correlation coefficient of 0.5 to guess this son's height. To do so, we just have to remember what the correlation coefficient means. For each standard deviation that the father is above his group's mean, we'll guess that his son will be 0.5 standard deviations above his group's mean. Let's think about this. The first question we must ask ourselves is, by how many standard deviations does this father exceed the mean height for all fathers in the study? In other words, what is this father's standardized score for height? Well, his height is 72 inches, but the mean height for fathers is 67.7 inches, so we'll subtract that off. And to finish standardizing, we must divide by the standard deviation for fathers, which is 2.7 inches. Run that through your calculator, and you'll get approximately 1.59. That is, the father is about 1.59 standard deviations above his group's mean. Hence, we'll guess that his son is some number of standard deviations above his group's mean. But what is that number? Well, the father is 1.59 standard deviations above the mean for fathers, so the number we want is half of that. Now, half of 1.59 is 0.795, so we'll guess that the sun is 0.795 standard deviations above his group's mean. Thus, our best guess for the sun's height is easily calculated. We start with the mean height among all the suns, which is 68.7 inches, and then we just add on 0.795 standard deviations. These are, of course, standard deviations among the suns, which is why each full standard deviation is 2.8 inches. Run all that through your calculator, and you'll find that our best guess for the sun's height is 70.9 inches. And we're done. The calculation we just did shows us a little of what's going on under the hood of the regression line and how it relates to the correlation coefficient. In fact, if we start on the horizontal axis, the father's axis, at 72 inches, the regression line will take us up and over to a sun's height of 70.9 inches. Obviously, this does not mean that every 72-inch father in this population had a 70.9-inch sun. It means that on average, 72-inch fathers have 70.9-inch suns. The actual heights of such suns varies quite a bit. That being so, you might wonder what the point is. The key idea is that this guess of 70.9 inches is an improvement over what we might call the naive guess of 68.7 inches. This would be a naive guess because it's just the mean height among all suns in the study. But if all we knew was the information in our table, that naive guess would have been the best we could have done. Yet remarkably, just by adding one number, the correlation coefficient between fathers' and sons' heights, we were able to improve upon that naive guess considerably. This will be easier to see if we restrict our attention to the strip of data corresponding to 72-inch fathers. More than 90% of this data lies in a still more restricted range. Let's just focus on this typical data, forgetting about the few oddballs on either side. We can now see that our naive guess of 68.7 inches is a pretty lousy estimate. A lot of even the typical data is quite far above our naive guess. On the other hand, our improved guess that we obtained from regression, that is by using the correlation coefficient, cuts right into the heart of our typical data. Of course, there's still plenty of variation around our improved guess, since the son's height is determined by more than just his father's height. Other obvious factors include his mother's height and his nutrition, but still, by taking the father's height into account, we've been able to recalibrate our guess. The effect of our recalibration was pretty substantial because the correlation itself was fairly substantial at r equals 0.5. For weaker correlations, closer to r equals 0, the improvement isn't as dramatic, and if r equals 0, there's no improvement at all. On the other hand, as r gets closer to 1, or minus 1 for a negative correlation, the improvement that regression imparts to our guesses becomes more and more impressive. Anyway, let's look at another historical example drawn from Pearson's own data. Instead of looking at the heights of fathers and sons, Pearson considered the heights of husbands and wives. Once again, I'll compile his basic findings in a table. When Pearson examined the husbands in his study, he found that their mean height was 68 inches with a standard deviation of 2.7. When he turned his attention to the wives, he found a mean height of 63 inches with a standard deviation of 2.5 inches. So far, so simple. This becomes more interesting when we consider the husbands and wives as pairs. After much patient calculation that today would be done on a computer, Pearson determined that the correlation coefficient relating husbands' heights and wives' heights was 0.25, which is a small but noticeable positive correlation. To ensure that we understand what this means computationally, let's consider a few simple questions. First, if we pick a random woman from the population from which Pearson drew his sample, what's our best guess for her height? Well, if she's picked at random and we know nothing about her, our best guess is the naive one. We'll guess that she's the average height for wives, which is 63 inches. Now here's a more interesting question. If we're told that the woman's husband is 65 inches tall, should we adjust our guess? And if so, how? Well, now we have some useful information. The husband's height is useful to us because we know how husbands and wives' heights are correlated. We know that for each standard deviation by which one of these variables exceeds its mean, the other variable will, on average, exceed its mean by only 0.25 standard deviations. This, of course, prompts us to think, okay, how many standard deviations above the mean is her husband? Well, he's 65 inches tall. Subtracting off the mean husband height of 68 inches and dividing by 2.7, which is the standard deviation among all husbands, we obtain negative 1.11-ish. In other words, her husband is 1.11 standard deviations below his group's mean. Hence, we'll guess that the woman is about some number of standard deviations below her group's mean. But what is that number? It's not 1.11. It's only 25% of that, which works out to about 0.28 standard deviations below her group's mean. Thus, our best guess for the woman's height is found as follows. We start at 63, which is her group's mean, our naive guess, as it were, but we'll adjust this guess by subtracting off 0.28 standard deviations. And among the wives, each standard deviation is 2.5 inches. Run that through your calculator, and you'll find that our best guess for the woman's height is 62.3 inches. Thus, the extra information about her husband's height led us to adjust our guess from 63 inches down to 62.3 inches. I haven't drawn a scatter plot, but in your mind you can imagine that among the 65-inch men, the average height of their wives is 62.3 inches, though of course there would be plenty of variation around this value. Another question about this particular example. If we pick a random husband from the population, what's our best guess for his height? Well, we have nothing to work with here, so we can only go with our naive guess of 68 inches, since that's the mean height of all husbands. But now let's suppose that we learn something. We learn that his wife is 68 inches tall. Should we adjust our guess? Well, of course we should, because we know how wives' and husbands' heights are correlated. This man's wife is tall relative to her peers. In fact, at 68 inches, she's 5 inches taller than the average wife. And since the standard deviation among wives is 2.5 inches, the man's wife is a full 2 standard deviations above her group's mean. Hence, we'll guess that the mean is some number of standard deviations above his group's mean. That number is not 2, but rather 25% of 2, since r is 0.25. This works out to half a standard deviation above his group's mean. Thus, our best guess for this man's height is found by starting at 68, our naive guess, and then adjusting it by adding on half of a standard deviation. Among the husbands, each standard deviation is 2.7 inches. Working that out, we find that our best guess for this man's height is 69.35 inches. Good, and note that we've used the same correlation coefficient to guess a wife's height from her husband's and a husband's height from his wife's. There's no direction associated with the correlation coefficient. It works both ways. Okay, correlation and regression, which is really just the other side of the same coin, is often misunderstood because our minds struggle with subtle statistical ideas about general tendencies. Instead, evolution has predisposed us to think in terms of causes. But correlation need not have anything to do with causes, as we've discussed already. Another, more interesting example will make the point well. Suppose you hear the following. Highly intelligent women tend to marry men who are less intelligent than themselves. This happens to be a true statement. I encourage you to pause the video for a minute or two and just turn this statement over a bit in your own mind. See what kinds of thoughts arise. Okay, did you do it? If you're like most people, you might have wondered if it is really true. It is. You might have thought about highly intelligent women you know and thought about their husbands. And you probably asked yourself something such as, what causes them to do this? What causes them to marry men who are less intelligent than they are? Depending on your own personal biases, you might have even suggested some causes. Some of you might have proposed that this happens because many men feel insecure around highly intelligent women and thus wouldn't want to marry them. Others might have proposed that this happens because highly intelligent women are the insecure ones who prefer to lord it over a less intelligent husband rather than face intellectual competition in their own homes. Who knows? And I'm sure you can imagine quite a heated argument developing between these opposing viewpoints. Such an argument might or might not be interesting, but psychological or sociological explanations are also completely unnecessary to explain why the statement is true. We don't need psychology to explain why, if you and I each put an apple on a table, there will be a pair of apples on the table. And we don't need psychology to explain why highly intelligent women tend to marry men who are less intelligent than they are. In the case of the apples, this is just a reflection of the mathematical fact that 1 + 1 is 2. In the case of the women, this is ultimately a reflection of another mathematical fact. The correlation between spouses' intelligences is not perfect, and thus is less than 1. To understand what this has to do with anything, let's go back to Carl Pearson and his married couples. Let's pretend that Pearson had given all his subjects some sort of intelligence test, and that he paired the wives' scores with their husbands' scores. He could then form a scatterplot with the results. This one surely looks plausible, a lot of variation, but a general upwards trend. The correlation coefficient will clearly be positive, and of course it will be less than 1. And as I said before, that upper bound is all that really matters for our purposes here. For the sake of definitiveness, let's pretend that r turns out to be 0.4. But again, as you'll see, all that matters for this argument is that the correlation is not perfect, that it's less than 1. So let's remind ourselves of what this correlation coefficient of 0.4 tells us. It tells us that, however far above average a woman is, the typical husband for women of her intelligence is only 40% as far above average. So for example, if a woman is 2 standard deviations above average, then a typical husband for a woman of her intelligence would be only 0.8 standard deviations above average. That's still intelligent, but not to the same extent as she is. I'm assuming, by the way, that men and women have the same average intelligence and the same standard deviation. And that is the idea in a nutshell. There's nothing special about the particular value of r other than the fact that it's less than 1. If, for example, r turned out to be much lower, say 0.08, the same basic idea would still apply. Only now that correlation coefficient would be telling us that however far above average a woman's intelligence is, the typical husband of a woman of her intelligence is only 8% as far above average as she is. And similarly, if r turned out to be much higher, say 0.75, then a typical husband would be only 75% as far above average. The specific numerical value of r doesn't matter. Simply because r is less than 1, it follows that however far above average a woman's intelligence is, the typical husband for a woman of her intelligence is just a fraction as far above average as she is. In fact, if we return to the original statement, we should now be able to see that we were tempted to psychologize mainly because of the things that were needlessly emphasized in the statement. For example, the statement refers specifically to highly intelligent women, which adds a little spice to the statement. What is it about those sorts of women? But in fact, our more sober analysis emphasizes that this holds however far above average a woman's intelligence is. Thus, we can replace highly intelligent women with a much broader category and note that women of above average intelligence tend to marry men who are less intelligent than they are. Their typical husband is still above average, but closer to the mean than they are. This revised statement includes the original one as a special case, yet it still feels a little spicy because it's a statement specifically about women. But remember, a correlation coefficient works both ways. Instead of using it to predict husbands' intelligences from those of their wives, we could use it to predict wives' intelligences from those of their husbands. Nothing in our analysis changes, which means that we can simply reverse the sexes in that gray box. And as a result, we see it's also the case that men of above average intelligence tend to marry women who are less intelligent than themselves. Once again, the fact that the correlation coefficient is imperfect means that data lying above the mean tend to be paired with data lying still above the mean, but closer to the mean. This has nothing to do with distinctions between the sexes. It also has nothing to do specifically with above average phenomena. If, in the gray box, we were to trade the word above for below, it would still be true, according to what we've learned about the correlation coefficient. For example, if r happened to be 0.5 and a man is 1.2 standard deviations below average intelligence, then a typical wife for men of his intelligence would only be 0.6 standard deviations below average. Still below average, but once again, closer to the mean, not as far below average as he is. Thus, we can say that men of below average intelligence tend to marry women who are more intelligent than they are. And of course, we can swap the sexes here too, and conclude that women of below average intelligence tend to marry men who are more intelligent than themselves. So in general, an imperfect correlation means that data lying away from the mean, either above or below it, tend to be paired with data that lies closer to the mean. This general phenomenon, in any imperfect correlation, not just this one, is referred to as regression to the mean. We've already seen this phenomenon in earlier examples, though you might not have noticed it. We saw that tall fathers, for instance, tend to have sons who are also tall, but not quite as tall relative to their peers. Short fathers tend to have sons who are also short, but not quite as short, again, relative to their peers. This is just regression to the mean. It was this observation, in fact, which Galton originally called regression to mediocrity, that gave the regression line its name in the first place. We will do well to remember that regression to the mean occurs because r is less than 1. Very well, but the natural question to ask is, why must the correlation coefficient always be less than 1 in any set of paired data? Why can't we have a correlation coefficient of, say, 1.2? Unfortunately, this is too difficult to explain in this introductory course. To explain it, we'd first need to discuss exactly how the correlation coefficient is defined. That part isn't too hard. And then we would have to do a lot of unilluminating algebra to prove that it can never exceed 1. Actually, if you know a little bit about vectors, including the so-called dot product of two vectors, you can prove that r is less than 1 without too much trouble. But alas, with ordinary algebra, the proof is exceedingly tedious, so I'm afraid you'll have to take my word for it. Or better yet, learn some more mathematics and then take a more advanced statistics class in which you will see a proof. Finally, I should mention that the example I gave about highly intelligent women and their husbands came from Daniel Kahneman, who mentions it in his excellent book, Thinking Fast and Slow, which contains a surprising amount of probability and statistics for a popular book on psychology. In particular, Kahneman has much more to say about regression to the mean, so do check it out. And that, my friends, is the end of this lecture.